Hi folks, in this lecture we're going to be taking a look at the laws of logs and then how do we solve more complex functions that would have several log terms in them. So first of all we just take a look at these are the laws of exponents of powers when we're multiplying powers. As long as they have the same base we can add the powers. Now it's the same here, both of these terms have the same base. Here they've been multiplied and then they've been added. So there's kind of an equivalence between the exponential laws and the log laws. But we'd expect that because they're essentially the inverse of each other. So we'd expect some term of equivalence. Here's two terms being divided. And we can see we can subtract the powers. Here we have two log terms being divided and we end up subtracting the log terms. So there's an equivalence then, and same with the laws of when we raise a power to another power, we multiply them. And here we have a value being raised to a power, but then we can just simply multiply it. So these are the three laws, logs 1, 2, and 3. And we'll generally be using them for the start of the lecture. We'll be more using them in starting with this and going to the left of the function. So we'll be using the log terms, the log laws, to compress. We'll be going from having two log terms and we can compress them into one. Here we have two log terms, we compress them into one. But note in rule 1 and rule 2, there's no numbers in front of their logs. They're what I call clean logs. So often we have to use rule 3 first, that if we have a number in front of a log, we clean it up first using rule 3. So probably best explained by example. Here's our 3 rules. So this is the way I'll be using them. You can see I've just inverted the order. Go from 2 logs to 1, 2 logs to 1. But rule 3, if there's a number in front of the log, we can bring that number up as a power. And now we have a clean log, which it allows us use rule 1 and 2. So these rules will appear beside each problem as we work our way along. And these are the problems we encountered in semester 1, where we're trying to compress two log terms into a single log expression. There's no equal sign here, so we're not solving anything. We're just simply compressing the terms. So we take a look. The second term is clean, as I said. There's no number in front of it. But this term here, we can see, well, we have the log, 3 times the log of 2x. So I'm going to bring, using rule 3, I'm going to bring that 3 up as a power. But what's vital to recognize is the 2x is in brackets. So our first step, there's the 2x, and the 3 goes up as a power. So that's rule 3 enacting there. And there's no change to the second term. Now remember, if we have ab to b squared, each part of the term gets squared. So it's the same here. We have the 2 is going to get cubed. Be careful. So we're going to have the log. Essentially, it's going to be 2 cubed x cubed. But 2 cubed, be careful, it's not 6. 2 by 2 by 2 is 8. The second term is still unchanged. And now we have clean logs. There's no numbers in front of them. They're being subtracted. So we're going to use rule 2. So this will now look like this is A, this is B. So we now have the log of A, the first term. Sorry, there's a squared there. I was just double checking and I noticed that. I'm sure you lot were all shouting at the screen. So this is now our new log term. Now we've gone from 2 terms to 1, which is what we wanted. Then numbers do what numbers do. 8 divided by 4 is 2. And powers do what powers do. We have x to the power of 3. We subtract the lower power. That gives us x to the power of 1. We normally don't write the 1 on the power. And what's really important to understand is even though they look completely different, these two expressions are equivalent. They're the same thing mathematically. In the same way as if I said to you, most people would agree 5,000 over 10,000 is the same as a half. Even though they look completely different, they're the same thing. It's exactly the same here. In terms of doing maths, this expression at the bottom is an awful lot easier to work with than the expression at the top, and that's why we do it. We look at another example. This is a little bit more complicated. Lots of numbers at the front, so we need to clean these up first. So we'll write that line. Now I always put brackets around, so the 2 comes up. The 3 is going to come up as a power. Now again, always put in brackets. Don't just write. The most common mistake people will make is write it as 2x cubed like this. But it's not. It's 2x to b cubed. And here we have 2, obviously we'll be bringing that 2 up. And now again, it's 2x squared in brackets to b squared. So now we'll multiply out our brackets just to tidy things up. We have 2 cubed again. This will give us the log similar to the last example, log of 8x cubed. Again, the 2 is squared, which gives us 4, and then x squared is raised to the power on 2, which gives us x to the power of 4. So now what I'm going to do is just simply rewrite things very quickly. Now you guys don't need to rewrite it, I'm just kind of laying things out. I'm writing my 2 positive terms beside each other. And I'm just going to leave the negative terms sitting out at the end just for a moment. So I've just rearranged the equation to bring my 2 positive terms together. And now I can use rule 1. Now you don't have to do this, but I find it makes the maths a little bit easier. Now we're using rule 1. Log of a plus log of b becomes the log of a by b. There's our a and there's our b. So we've now got the log of x squared by 4x to the power of 4. This other guy is still waiting his turn. And now we just multiply out our brackets. Again, numbers do what numbers do. 1 by 4 is 4. X to the power of 2 by x to the power of 4 is x to the power of 6. And now the kind of negative term can be brought into play. Just double checking everything, try and quickly make sure I haven't made any terrible errors, which I often do. Okay, so yeah, that's just to tidy up. Everything looks okay. So now we use rule 2, log of a minus the log of b. Remember, whichever term is first always goes on top. Now, numbers do what numbers do. This will give us a half. 4 over 8 is a half. And then we have x squared on the top. Finally then, I'm just going to write that as fractions. We can tidy everything up. Top by top will give us x squared. And on the bottom gives us 2. And that's the neatest way then. That's the way the answers would be written in the quizzes. Cubed. Sorry guys. I was more worried about running out of space, so that should be a cubed there. Please forgive me. It's very easy to kind of make a simple slip, so it's always good just to check as you go along. You can see me doing it. There's quite a lot of maths going on here. It's very easy to make a simple error. So kind of it's always good as you move on through one or two lines, just go back and check that no errors have crept in. Now I'm checking again just to be doubly sure. I think everything is okay. Okay. So now here's a question for you to try. So have a go at this. Simplify this to a single log expression. And simplify this one to a simple log expression. So again, pause the video, give those a go, we'll push on. Now what we're going to do is kind of bring in the skills from the previous lecture where we were solving log equations for x. But now there'll be several log terms. So the first thing is we cannot switch off that natural log. We cannot move in straight away, raise both sides as a power in e and hope that the e will go in and kill him and kill him. Doesn't work like that at all. Really what you'd get is e to the power. If we did that, if I raised both sides, what I'd simply have is on the left I would have e to the power of all of this is equal to e to the power of 1.25. This thing here is impossible to solve because you've got an exponent and a log in the same expression. You can't go forward, you can't go back, you're in kind of a mathematical cul-de-sac. So trying to kill the natural logs first of all will not work. We have to compress them until we have a single log term, and then we can bring the e into play. So even though these are natural logs, it's still the same idea on the left hand side. I'm going to clean up the second term. So first term is unchanged. Now the 2 goes up as a power. So that's using rule 3 first of all. Now we can use rule 2. We've 2 clean logs been subtracted. So this will give us a and a little bit of maths if you want. You can write a 1 there. Numbers do what numbers there do. 2 divided by 1 is 2. X cubed divided by x squared. 3 minus 2 leaves us x to the power of 1. Again, you normally don't write that 1. And now we're on more familiar ground. We want to solve for x. We want to kill the natural log first of all. Raise both. So this is where we can bring the e in, is when we have a single log term, or a single natural log term in this case. Raise both sides as a power on e. When we do it to the right, we get this. On the left hand side, guys, I'll just write it briefly. This is what happens. They cancel each other out because they're inverse, which is what we wanted to happen. Now normally we would just go from this line to this line. And now we can divide both sides by 2. And it's simply a calculator exercise then. Divided by 2. And we get x is equal to 1 point. I should have actually, I'm just going to quickly run back and double check I haven't made any mistakes. Okay, looks okay. Yeah, I think that's okay. So again, take your time, double check. It's always good policy. Especially when you're doing the quizzes, like there's nothing worse, as you know by now, there's nothing worse than getting 9 out of 10. Well, I suppose getting 1 out of 10 would be worse, but here's another one. So again, we're going to use rule 3 to clean up the logs first. The log of 3x to be squared. Now be careful, each term gets cubed, so that becomes 2 cubed. Here now 3 is to be squared, so each term again gets squared, so 3 squared is 9, x squared. So very easy to make a mistake going from the first line to the second line. Double checking everything's okay. Now we use rule 2, the log of A divided by B. So now I need to kill log. What's the inverse of log? Is 10 to the power of. We raise both sides as a power on 10. So that's the left hand side been raised as a power on 10. When we raise the right, sorry, that's the right hand side been raised to a power of 10, forgive me. When we do the same to the left hand side, it just kills the log. I should have tidied this up a little bit. Sorry guys, I'll just go back to this line here. When I tidy up, sorry, I forgot to cancel the x's. We get the log of 8 over 9, and we just have an x left, really. Numbers do what numbers do, powers do what powers do. And sorry, I should have killed the log. So now we're nearly there. Sorry, I kind of hope that hasn't confused you too much. I think we're okay though. Now we just want to get rid of the 8 over 9. We're going to divide both sides by 8 over 9. But remember, when you divide by a fraction, it's the same as multiplying by its reciprocal. So we can now multiply the right hand side by 9 over 8. Again, you could divide the right hand side by 8 over 9, but you will mathematically end up with this. It'll just take a step or two longer. And now we can just get the calculator. So 9 divided by 8 by and this gives us 647. We'll just say 0.4. Just double check that again. So just so we get the same answer. So again, take your time guys, there's plenty of room for error. Again, I'm just double checking I haven't made a mistake. I don't think I have. So now, here's some for you guys to try. Pause the video. And it's the same principle, just be careful. And actually guys, I've just kind of realized this should be, oh no, that's okay, sorry. Yeah, so just give that a go. Now you might need to do a little bit of maths to get there, but now just take a note of this problem. If you look back in the previous lecture, I think you would have worked this out. So remember to bring him over to the left hand side first of all. And then if you look back through the previous lecture, lecture 13, hopefully you'll have worked that out. So that might save you a little bit of effort there, but just be careful. No harm in doing it all again either. So now we just take a look at some more complex problems. I know you're probably thinking it couldn't get any more complex, but it can. So now we have two log terms, but there's a bit going on in the second bracket. So remember, they're being added. So using rule 1, we would get this. Now you can either multiply, I kind of tend to multiply out the brackets first, but that's just me. Or alternatively, you could have killed the log first, which would also be valid, but I'm going to do that second. So we raise both sides as a power on 10. we just get x squared plus 3x is equal to 10 to the power of 1. So I'm going to bounce the 10 over. We'll just get rid of the power. We don't need it. Subtract 10 from both sides. And we've got x squared plus 3x minus 10 is equal to 0. This is a quadratic, guys. I'm not going to spend ages kind of going over it. So when we factorize this, we're going to have 5 and 2. The positives win out, so plus 3x, so that's going to be a positive, that's going to be a negative, double check. X squared minus 2x plus 5x equals 3x minus 10. Yep, everything is okay. And now, when we let each bracket equal to 0, we get x is equal to 2, and x plus 5 is equal to 0. So these are our two answers. But remember from our graph, lecture 13, you can't get the log of a negative number. So if I was to feed this answer back into my original equation up here, I'd have the log of minus 5, which cannot be found. So this answer is invalid. So there's only one answer, and that's x is equal to 2. The other answer is mathematically kind of there, but it doesn't satisfy this particular function. Another tricky one. So first step, using rule 1. There's no numbers in front of them, so we don't have to clean up any logs. Sorry, I'm jumping ahead of myself. Now this time I'll kill the log first, just to kind of show it doesn't, you know, I'm going to raise both sides as a power on 10. And this will give me, so x plus 2, x minus 2. You might remember these from semester 1, the difference of two squares. You can multiply them out using FOIL. First outer, inner, last. But I recognize this is the difference of two squares, so when we multiply them out, we're going to get x squared minus 4. I might just do that out just to be double. I'm sure some people are scratching their heads, so I'll just quickly do it out. So remember FOIL. F first terms, x by x, so x squared. The outer terms, O minus 2x, x by minus 2. The inner terms, plus 2x. And the last terms is minus 4. So now, these will cancel each other out, which gives me my difference of two squares. X squared minus 4 is 10 to the power of 1.3. I can move the 4 over, add 4 to both sides. And finally then, I can get the square root. Remember, don't be too keen to dive for the calculator straight away. It's much more professional to only do your calculation at the very, very end, because you're only rounding up once. If you keep hitting the calculator at each stage, you might have 4 or 5 roundings by the time you get to your answer, which will have an impact on your accuracy. Plus 4. Square root of 10 to the power of 1.3 plus 4. And we end up with x is equal to 4.8941. The question will usually say to specify to a number of significant figures. So now there's just a couple of problems for you to try. Don't forget to pause the video first. This one is similar to the one we just did 2 slides ago. Just be careful when you work everything out. You'll have to factorize a quadratic to get to your answer. Check for positive or negative answers. And then this problem here is a little bit more challenging. Don't let it put you off though. When you're multiplying your two terms, these are going to end up in multiplied. If you're unsure, just write the first one as a fraction, and then you have top by top, bottom by bottom. Then you can kill the natural log and solve carefully from there. That second one is quite tricky. If you can solve that one out, you're kind of well able to deal with log functions. Just to kind of give us a feed into where we're going next, so that's kind of the problem solving part of logs, and now in the next lectures we're going to explore where these skills are applied. So first we'll be looking at the Richter scale. So the Richter scale is a log scale. Here's the formula for it. And each successive value on the Richter scale represents a tenfold increase in magnitude of movement. So a Richter scale that measures 7.2 will be 10 times stronger, will be 10 times the magnitude. In other words, the Earth would move 10 times by a greater distance than a Richter scale of 6.2. So there's a tenfold increase as you go up by one on the Richter scale. It represents a tenfold increase in magnitude of movement. So that's one area where logs will be used. We'll be looking briefly at that, probably not doing a lot of maths, but taking a look at some of the concepts. Then we'll be looking at the decibel scale. Again, it's a log function. So a 10 decibel sound is 10 times more intense than a 0 decibel sound. 20 decibel sound is 100 times more intense than a 0. A 0 decibel sound is the quietest noise, the quietest noise the human ear can hear. So we can see there's this log relationship as well. Now really a decibel is 1/10 of a bell, but we'll get into that when we look at decibels next week. And here's an example of the decibel scale. So it's not linear. And this is the threshold of pain. So this is the loudest noise you can hear before your eardrums kind of physically rupture. And this is the quietest noise. So the decibel scale goes from 2 decibels up as far as 140 decibels. If we were just to talk in terms of what the human ear can hear, the quietest noise the human ear can hear is 20 micropascals. The loudest noise, now it can get bigger than this, but it's about 200 million micropascals. So that's the scale of human hearing. And this is why we use logs to compress that. It's just the numbers are too big for people to kind of comprehend. So we compress this huge scale using logs. Now initially the compression just brought us to the bell, and the bell just went from 0 up as far as 14. It's a little bit like the pH scale. But that was considered to be too much of a compression. So they divided each bell. They said, right, there's 10 decibels in each bell, and that brought our scale then up to kind of a more reasonable from 0 to 140. Finally then, this is just saying anything above 90 can cause permanent damage to hearing. So this is for health and safety, guys. There's all sorts of legislation to protect workers when they're exposed to loud noises for a long period of time. Finally then, the pH scale. And this again is another log scale. We're comparing the number of hydrogen ions to the number of hydrogen ions in water, which is actually 1. We don't normally write that 1 though. And then this is your typical pH scale. It goes from 1, which is very acidic, to 14, which is very base, very alkaline. Now, to be perfectly honest, most of you guys are going to know a lot more about pH than me, but we'll just take a look at the maths of it when we're in the following lectures. So I'll finish up there, guys. Thank you very much again for listening, And as I said, in the next two lectures, we'll explore these three logarithmic scales.